Hello and welcome to Monday's edition of Cracking the Cryptic, where Mark has sent me a puzzle to try today. I've had a quick look at the rules before I turned on the webcam, and frankly, this one feels ludicrous. It's called Set by ICHTUES. But unless I'm missing something, the set in question is not the normal Sudoku sets that we've become familiar with, things like the proof of the Fistomerfell ring. This is a different creature altogether. It's to do with entropies and modularities, and you can see from this grid there's almost nothing in it. There really is almost nothing in it, but there is the horrible disjoint subset rule today, which is this weird rule where, say that digit is a 6, that digit couldn't be a 6 because that cell is in the same relative position of its 3x3 box. It's sort of the midwest point of the 3x3 box. So these digits, the midwest points of of each 3x3 box, have to contain different digits in the puzzle, and I find this so difficult to scan. But anyway, that exists in this as well, but it's a mad rule. I did find it on Logic Masters Germany, where it's got 4 stars out of 5 for difficulty, yeah. Anyway, I'll read the rules properly in a moment or two's time, but this might not become videos. It's one of those puzzles that I suspect if you don't see the trick, you'll never solve it. That's my prediction. Now, I hope I will solve it. I hope that you're watching this video thinking, oh, he's going to be able to solve this. But you might not be. And anyway, let me look at my list of things to do. I should mention, in only a couple of days' time now, we're going to be streaming again. We're going to be having a look at Monument Valley, this very beautiful looking game that several of you have suggested we try. And I've actually got Monument Valley 2 as well, because some people have said we might find Monument Valley too easy. Now, I'm quite sure that isn't the case. If you've ever watched our prowess at these games, unless they involve sort of arch logic puzzles, we tend to be fairly terrible at them. So anyway, we're going to be doing this 10 p.m. UK time on Wednesday. Love to have your company if you're around. Over on Patreon, we have got, of course, our new Sudoku hunt themed on April Fools. Loads and loads of you having a go at that and enjoying it, which we're absolutely delighted to see. I haven't got it today. I quite often like refreshing the league table to see how people are doing, but I haven't got it. I haven't got it on my screen for some reason, so I can't do that today. But anyway, do check it out. You will enjoy it. It's a couple of bucks to join us on Patreon if you're not already patrons. I guarantee you it's the best value $2 you will ever spend. In terms of sort of joy percent, you basically can't beat it. It's impossible. Hours of joy percent would be a better way of describing it. And I've got a birthday to do today for Colby. Colby, it's your birthday, and I know this because your partner, Reign of Terror, wrote to us and said rather charmingly that you never ask for much for your birthday, Colby, but Reign of Terror thinks that you will really enjoy a shout out. Well, I hope you do. I hope that you have a great birthday today. I hope you get some chocolate cake, which is full of icing and extremely heavily iced, and many happy returns. And that is all the news. So why don't we turn our attention to Set by ICHTUES, and I will read you the rules of this one. We've got normal Sudoku rules apply, so we're going to have to put the digits 1 to 9 once each in every row, every column, and every 3x3 box. Digits along a marked diagonal cannot repeat, so those cells are going to be the digits 1 to 9 once each. These cells are going to be the digits 1 to 9 once each. Digits along an arrow sum to the digit in the corresponding circle. So look at this one here. If this was a 9, then these squares, I mean, we could make it up in a whole variety of ways. You could have something like 1, 1, 7. 7 plus 1 plus 1. Or you could have 2, 2, 5. Or you could have 1, 2, 6. So there's a whole wealth of ways to fill arrows, but that is one thing we must do. And then we've got the disjoint subset rule. So corresponding cells in each box must contain the digits 1 to 9. So hopefully that's clear. If you look at this cell, let's do this one. So that the equivalent positions are going to be all of those. And those digits, those green cells must contain no repeated digits. And same would be true for these squares, for example. Those all have to be different, etc. Now, this is where the rules go mad, frankly. It says, let a digit's entropy describe if it is low, 1, 2, 3, medium, 4, 5, 6, or high, 7, 8, 9. Let its modularity be its remainder when divided by 3. So let's just make sure we understand what modularity means. So the digits 1, 4, and 7 are all the same modularity because each of those digits has the same remainder when divided by 3. If you divide 1 by 3, it goes into it 0 times with a 1 remainder. If you divide 4 by 3, it goes into it once with a 1 remainder. If you divide 7 by 3, it goes into it twice with a 1 remainder. So they all have the same remainder. So 1, 4, 7 have the same modularity. 2, 5, 8 have the same modularity. 3, 6, 9 have the same modularity. And then it says, let a set which has capital letters be a set of 3 digits such that their entropy and modularity are either all the same or all different. I'm just going to read that sentence again. Let a set be a set of 3 digits such that their entropy and modularity are either all the same or all different. Then it says some examples of sets are 7, 8, 9. So 7, 8, 9 are digits with the same entropy, yes, and different modularity, yes, they all have different remainders when divided by 3, okay. 2, 5, 8, different entropy, same modularity, yes. 1, 6, 8 and 3, 4, 8, 1, 6, 8 and 3, 4, 8 have different entropy and different modularity. Yeah, okay. I'm going to give you a tip about this in a moment, but let's just complete the rules first. Because it then says, in this puzzle, the 3 rows and 3 columns of each 3 by 3 box all form sets. So if we look at this box, those 3 are in a set. So they could be 7, 8, 9. These 3 are in a set. These 3 are in a set. And those 3 are in a set. Those 3 are in a set. And those 3 are in a set. And that's true for every 3 by 3 box. And that's all the rules. I mean, it's crazy. It's just absolute lunacy. But I want to get to my trick. I've got one trick to tell you, and it's not even a good trick. I mean, if I was a magician, I'd never make any money at all, but I have a trick to tell you. So do have a go. The way to play is to click the link under the video as usual, but now I get to play. Let's get cracking. I'm going to talk about my trick, which is when you think about entropies and modularities, look at the number pad to the right of the that we're all solving with at the moment. Now, one way to think about entropic sets is that they are from, a horizontal section of the number pad, like 1, 2, 3, 4, 5, 6, 7, 8, 9. If you want to look at modularity sets, you could look at vertical sets, 1, 4, 7, 2, 5, 8, 3, 6, 9. And if you want to look at these ones which are described as different entropy and different modularity, what we could do there is look at the number 1 on the number pad, and if we're picking different entropies and modularities, we need to pick, so from the second row we need to pick a number that is not 4, because 4 is in the same column, so must share modularity. So we could pick 5, 1, 5, and then because we must have the final digit which can't share either entropy, which is horizontality or verticality, it must be 9. So 159, I think, is a set of numbers in this puzzle that is different entropy and different modularity. There, I've said it. So I'm sort of I'm doing it by madness, just by looking at the number pad and picking weird sets. Let's do another one. So okay, in fact, let's think exclusively about. Yeah. So I think actually there are only 4 sets involving the number 1. I might be wrong about this, but I think that's right, in the sense that the number 1 can be in an entropic set with the numbers 1, 2, 3. That's one option. In a modular set with the numbers 1, 4 and 7. That's a second option. In a non-entropic and non-modularity set, which would be, for example, 159 or 168. They are all the ways that one can form a set in the puzzle. So does that mean every number? Yes, it does. It means every number in the puzzle has 4 possible sets it can be a part of. Now, I don't know how they fit together, but that seems to me to be true. Oh, my phone is buzzing. That's fine, though. Right. So sorry, now I need to think about the rules again. So now I've worked out every number is possibly part. So if this was a 1, this set here, which must be a set, is either 1, 2, 3, 147, 159 or 168. And this one, which must also be a set, is also one of those, but it's obviously not the same one. So if that was 1, 2, 3, this one is either, I think it's still got loads of options, it's either 147, 159 or 168. Let's just make it 147 and think about it. So now this one, which involves 4, yes, okay, but that one is going to have to be 4, 5, 6 now. And the reason for that is that the other ways of joining 4 up in a valid set have all been ruled out, because we've only these digits here, we've only got to choose from the digits 5, 6, 8 and 9. And we know that this must either be a perfect set in the sense entirely modular or entirely entropic, or it must be entirely not have a repeated modularity or entropy. And the problem with that is, because 1, 2 and 3 are not available, effectively the top line of our number pad has been taken away. So the only way to construct a valid set is the 4, 5, 6 set. So that would be 4, 5, 6 in this instance, and this presumably would be 7, 8, 9. And then this one would be a 2 set. Now let me think about this. It couldn't. Oh no, hang on. Oh, I see. So that being 147 has the same property. This would have to be a perfect modularity set. It would be 2, 5, 8. This is quite interesting. I mean, I know this is not that, you know, other variations are possible, but by specifying this one and specifying that one, and of course this 4, 7 could be the other way up. You force the nature of the box. Okay, here's one thing I can see as a result of that. I don't know if this is going to help, but I can see it. You are going to get roping, I think. I feel like you're going to get roping. What do I mean by roping? What do I mean by roping? In fact, hang on. Let's just delete that. Let's just say we start with 1, 2, 3 here. I have to put 4 into one of these positions. And wherever the 4 goes, from a horizontal perspective, what set can it be part of, given it cannot involve a 1, 2, or 3? It must only be 4, 5, 6. Yeah, so if you do, anywhere in the puzzle, put a 1, 2, 3 set, either horizontally or vertically, in that box, the sets will be entirely entropic. So you'll mimic the entropy of the 1, 2, 3 in the other 2 lines. But you don't, I don't think, I might be wrong about this, I don't think you have to mimic the modularity. I mean, this one does have 1, 7, 4, which are obviously all from the same modular set, but imagine we shifted 8 there. 1 and 8 on my number pad require a 6 here. So this would be a possible set, that would be a possible set, and if you go 1, 8, 6 here, how does the 2 then work? 1, 8, 6, so the 2 would have to go, to make a set, it would have to go with 4 here. Okay, so that would be 4, that would be 5. I think this would be a 9 and that would be a 7. Now do these work? So if you had 1, 8, 6, yeah, all of the sets become sort of non-perfect sets. They are still sets as within the meaning of the puzzle, but they have different entropy and different modularity. But okay, but am I right that you get roping? So this is clearly a set. This is clearly a set. This is clearly a set. And this would have worked, obviously, if this had been 1, 4, 7, this had been 2, 5, 8, this had been 3, 6, 9. It would have worked. It's just, what I'm trying to work out is whether or not now... It does, yeah, it is necessary, isn't it? Because let's look at those 3 squares. Now they have to form a set. Go back to our number pad without using 7, 8, 9. So what sets are available? It's going to have to, the only way to construct a set now, if you can't use 7, 8, 9, so you're only using the top 6 digits of the number pad, and you either have to have them all in different rows and columns, which you can't have because 7, 8, and 9 have gone, or you've got to have them in the same row or column. So yes, we are going to get roping. By which I mean this one is either going to be 1, 2, 3. Let's say it was 1, 2, 3. Then this will be 1, 2, 3. These don't have to be in order, but this is just to show you the principle. Now 6, 4, 5 would have to go up here. So this would be 4, 5, 6, and this would be 7, 8, 9. And this would be 7, 8, 9. Again, the order of this is not specified, but you do get roping. And you're going to get roping in the columns as well by that logic. So what we've now deduced is what? Don't know. Not even sure. I think we can just delete it. We're going to get... I've proved that... Well, I think I've proved to my satisfaction there's roping. So whatever we put as the 3s here, are going to be duplicated in terms of if that's a triple, there's going to be a triple maybe there or there, and then that same triple will be horizontal in box 3 as well. And the same is true vertically. So this arrow has to be from a valid set. Well, I can see immediately 1, 2, 3 would work, wouldn't it? If that is a 3 in the corner, and this that may get confetti, it does, but we can't. I mean, there's going to be other options that work here. I'm sure there are. Although having said that, 8 is not equal to 2 plus 5, 7 is not equal, 9 is equal to 3 plus 6, so that would work, and this isn't even counting the different entropy and modularity sets. I was just in my brain there, I was just trying to think about whether if you had different modularity sets, whether necessarily the mathematics couldn't work, but it could work. So although it doesn't work with 1, because 1 sets are 1, 2, 3, which does have a valid solution for that arrow. 1, 4, 7, that doesn't. 7 is not equal to 4 plus 1. 1, 5, 9, 9 is not equal to 5 plus 1. And 1, 6, 8, that doesn't work either. 8 is not equal to 6 plus 1. So let me just, is it worth? It might be worth just sketching out the possibilities here in terms of, because I don't think there are that many. What I mean by that is if you do have, let's say that this box had a 1, 2, 3 triple here, then we know that the sets beneath it would have to be 4, 5, 6 and 7, 8, 9. So that is a possible way of setting out a box, i.e. there'll be a 1, 2, 3 triple, a 7, 8, 9 triple and a 4, 5, 6 triple, or vertically 1, 2, 3, 4, 5, 6, 7, 8, 9. This is one possibility. Now the other possibility, or no, that's not the other possibility, another possibility is that we preserve modularities rather than entropies. So to do that, we would have 1, 4, 7 as the one set, 2, 5, 8, 3, 6, 9. So that's sort of set possibility 2. And so what I'm saying there is, if you do have 1, 4, 7 as a set, then you are forced in one of these lines to have 2, 5, 8. You must do it. And again, the way I'm seeing that, I know I'm strange, and I'm happy to admit, and most people who've ever met me would say, yes, it is the case. He is a lunatic. I'm not really a lunatic. I'm just a bit strange. But what I'm doing is I'm looking at my number pad, and I'm imagining the numbers 1, 4 and 7 have disappeared off the side of it. So now I've got just 2, 5, 8 and 3, 6, 9. But I know if let's start with the 2, I could pick a 6, yeah? But then what other I now cannot pick a number from the same modular set, or I don't have a different modular setted. I don't have a set within the definition of the puzzle. So I've got to retain the modularity. I've got to go straight down the 2, 5, 8. So anyway, this means this would have to be 2, 5, 8. It doesn't have to be in that order. You know, you could have 9, 6, 3 or something. That would be totally fine as well. So, but that is another way of doing the puzzle. Now, if we go for the 159 version, 159. So imagine this is one. Well, let's do a funny one. 519. Now, if we're in 519 land, the 2, wherever that is in the box, it can't have an 8. So it's going to have a 7. 2, 7, and then it can't have a 4 because it's already had a 7, so it's going to have a 6. So 2, 6, 7 will be one of those. So this is 2, 6, 7, and that means that 3, 4, 8 for the other one. Yeah, they're all in different modular sets, so that's believable. Now, but there's one more, which is 1, 6, 8 for the 1. So again, if you have 1, 6, 8, let's do a vertical 1, 6, 8. Now, wherever we put the 2 in the box, what's that going with? 1, 6, 8. The 2 can't go with the 5, because if it went with the 5, it would then need to go with the 8. So it's going to have to go with a 4, and then a 9. 2, 4, 9. And that means 3, 5, 7 will be the final column. So 2, 4, 9. Oh, whoopsie. Sorry. 2, 4, 9. 3, 5, 7. So that is the full panoply. So every single box in this puzzle exhibits one of these characteristics, either vertically or horizontally. That is what I'm claiming. Now, so what is this arrow? 3, 2, 1 would work. That one would work. 9, 6, 3 or 9, 3, 6 would work. Nothing else works. Right. So this arrow is, this corner digit is 3 or 9. And it's either 3 with a 1, 2 pair or 9 with a 3, 6 pair. There is always a 3 on this arrow. So that is not a 3. Hang on. But if this was 3, 2, 1, dusty bin, that would be... That can be anything, because we're just adding a load of numbers along a diagonal. I mean, this would have to be at least... This does, ab initio, have to be at least 4. Because if these were minimised at 1 and 2 and that was a 1, then the arrow would add to 4. So that is at least 4. So the fact there's a 3 on that arrow doesn't actually reduce any possibilities for this. What the blazes are we meant to do with this? Hang on. Oh, the disjoint subset rule. But I haven't got anything in the grid. Sorry, hang on. Let me just mull this for a second. That... No. This is no, this is horrible. This is horrible. This doesn't do anything at all. Sorry, I know I've stopped talking. I'm rapidly reaching the conclusion I don't understand this puzzle. How on earth are you meant to do this? So, if this is 1, 2, 3, we're in this world. So this would either be 4, 5, 6 or 7, 8, 9. All of which are very possible for this digit. Hang on, there's something weird. This doesn't... I mean, I don't understand. So, oh dear, this is awful. I started to get those prickles of fear where I just feel like I haven't even got anything to say. I can't do any calculation or anything. There's just, it's just, I don't understand. So this one is definitely from either green or yellow. But that one, so I mean, if this was entropic, so let's say that was 3, 2, 1, then this one I think it can be any of them. I'm sorry, I just want to have a look. I'm just going to sketch this out. So if that's, just say that's 3, 2, 1. We get another 3 in the corner. This set here is obviously not 3, 2, 1. Could it be 3, 6, 9? So if this is 3, 6, 9, we know this will be 1, 4, 7. This will be 2, 5, 8. I don't think that's a problem. If this, on the other hand, is 3, 4, 8, let's just have a look at that. If that's 3, 4, 8, this has got to be 2, 6, 7. Oh, I see, but this is going to be, okay, but this is going to have to be entropic. So this is, yeah, okay, so that being, once you decide what that is, you know what this is now, and you actually know the order of it as well. Because if you go 3, 4, 8, because we know this is 4, 5, 6, and 7, 8, 9 in some order, once you go 3, 4, 8 here, you're in this world, so this one is 2, 6, 7. This can't be 7 because that's going to be a 4, 5, 6 triple. So you have to do that, and 9 and 5 is how it would have to look. And then then it works. You're in that world. You've preserved the sets vertically, and you've preserved the sets horizontally. And you are. Wait. Wait, you've also got sets diagonally. What the blazes has gone on there? Is that why? That's interesting, actually. I don't know if that's forced. That would be fascinating, because if that's true, if the fact you have to have sets horizontally and vertically, well, if you do have to have sets diagonally, that is a 9, which would be a digit in the puzzle. And the reason I would know that that was a 9 is that we've deduced that the only way of constructing a 3-cell arrow from sets in this puzzle is either 3, 2, 1 or 9, 3, 6, which always have a 3 on them. So that would have to have a 3 on it, and that would look at that cell along the diagonal, which couldn't be a 3. Right, so what we need to do is delete this, and we need to think about whether it's true. So let's look at the simple case. If we had 3, 2, 1, so if we had entropic perfect, if you had perfect entropy in the row and perfect modularity in the column, then we know this is 258, we know this is 147. Is it necessarily the case that that which would be 1 and 6, does that have to be 8? Sorry, and the reason I'm asking that is, 1, the sets involving 1 are those. So there's only one of those that contains 1 and 6, and it has 8 in it. So does that have to be 8? Why couldn't that be 7? Which it could be, because we know that this is 9, 7, 8. Oh yeah, but hang on, that doesn't... It does have to be 8, because 1, 8 is not a modular set. Yeah, okay, so if we... Hang on, let me try and do this using my number pad then. So what we're saying is, if we take perfect modular sets, yeah, I can sort of see that actually. So what I'm doing in my mind is I'm looking at a horizontal set as being, say, 3, 2, 1, and I'm running off the 1 a perfect modular set, which will be 1, 4, 7. And then I'm saying, okay, which isn't the example I've drawn in the puzzle actually, which is probably not sensible. So let's try and be on the same page. So I'm saying something like this. And I'm thinking about these populations of digits. Now we know that this is 258, and we know that this is 789, so we actually know that this digit is 8 now. And looking at our number pad, we can see that these digits are from 5, 6, 8 and 9, but they have to also obey the modular preservation rules. So if the 3 had been here, this digit would have been 9. But then that digit would have been 5, because this would have been the 258 modular set, and we'd have got 195 along the diagonal, which is still a modular. It's still one of these weird sets. Yeah, I mean, it's certainly true. If you've got perfect entropy versus perfect modularity, it's certainly true to say that you're going to have you're going to have sets in the diagonals. That I can see by looking at the number pad. But what happens if instead you have a more complicated creature? So let's say you had 159 here, and you offset that with a 168. I mean, so that is as horrible as it comes. 159 are all from different everythings, and 168 are from different everythings. Do you still, on this diagonal, so let's look at 159, 168. So the digits we're looking at here are from 2, 3, 4, and 7. But we know that because we're in the 168 world, when you're in the 168 world, the 9 has 2 and 4 hanging off it. So this is going to have 3 and 7 hanging off it. And what is the set here? Again, the set that you have to preserve the integrity of the set. So once you have 159, you're in this creature. So this 6 is going to be accompanied with 2 and 7, so that everything gets fully specified, and you've got 1, 7, 4 on the diagonal, which is perfect. It is a set. Yeah, okay. So this is it. This is it. This is the trick in this puzzle, and it's very hard to see. Well, no. It's going to... I know everyone watching this has already understood this. And I apologise for my inability to articulate it. But the way I am seeing this in my brain, let me try and succinctly state it, is the following. Every digit corresponds, is in one of the, so let's pick the number 4. 4 is either in this set, this set, this set, or this set. But whichever one it's in, let's say it was this one, horizontally. Then the other numbers in this box have to obey these principles. So if you had 3, 4, 8 here, one of these is 2, 6, 7, one of these is 1, 5, 9. We don't know which way round it would be, but that is true. Now similarly, once we've got the 4 specified in the row, we've got to pick a different colour for the 4, how the 4's working in the column. And whichever one you pick, you're going to force, if you like, the verticality. So if we were pairing this one in the row with this one in the columns, can you see that the 2, for example, in this grid is going to be part of a 2, 5, 8 vertical and a 2, 6, 7 horizontal, wherever it goes? And if you sort of stare at the number pad and you think that you specify the 4 and you look at which sets that's in, and you specify the 4 and you see the numbers that you've got left and how they interact, you can see that the crossing is always going to be from a valid modulus, or not a valid, no, it's always going to be from a valid set, not a valid modulus set necessarily, but it might be a valid modulus set, i.e. it might be 3 digits of the same modularity. And the way I'm seeing that is I'm looking at the number pad, I'm crossing off the numbers I've decided are in the row for a particular number, I'm crossing off the numbers that I feel are in that numbers column by choosing another of these sets, and then I've got 4 numbers left for the balancing. So say this is the 4 here. Let's use this example. So we'll go 3, 8 here, we'll go this one, shall we, 1, 7 here. Okay, so we know that because we're in 4, 7, 1 land, we've got 3, 6, 9 here. Because we've got 8 here, we must have 2, 5 here. But in the rows, we're in these ones. So the 1 is going with 5, it's going with 9. That makes this 6, and that's 2. Look at the diagonals. You've always got sets. Sorry, my voice is still slightly giving out. So whether you do it by exhaustively proving it, or do it by looking at the number pad in your head, this is massively, well, it's going to help me to get a digit in the puzzle. In fact, it's not a 3 in the corner, is it? Bobbins. Because now I know that every single one of these boxes has has 2 diagonals that obey the principle. So this has a 3 on its arrow, and that digit in the corner is a 9, and therefore the 9 is joined by the 3, 6, so we're in this one. Which means that, well, this has to be 3, 2, 1 now, because the digit in the corner can't be a 9 by the diagonal rule. So this is going to be, that's 3 in the corner, that's 3 in the spotlight, losing its religion. This is great. Now, okay, so this is a valid set, which is not 936. It's not 924. There's already been a 2 on the diagonal. It's not 915. There's already been a 1 on the diagonal. So it is 978. Therefore, these squares are 4, 5, and 6. Just to complete this diagonal, which of course is another valid set. I'm hopeful now. We might be able to do the puzzle. Now, what's that digit then? Well, we know that we're in these worlds, aren't we? So that digit. Okay, this digit is not a 4. Because if it's a 4, we're in this world, in this box, 1, 4, 7. And there's going to be a 1 in one of those squares. And therefore these will add up to more than 4. So that's not 4. It's either, it might be able to be 5. It's either 5, 7 or 8. Okay. Oh, here's a beautiful point. It can't be 5. I mean, actually, I love this reason. There may be a different reason, but I've got a very nice reason. Look at the sets involving 5. And in all of them, is 5 the smallest number? And the answer is no. There's always a higher number than 5 in all of those sets. So if 5 was here, one of those numbers is higher than 5 and the arrow can't work. So that's definitely not 5. This is 7 or 8. Now, if it is 7, if it's 7 here, this would be 4, 1, wouldn't it? I'm actually just going to pencil this in so I can see it. 7. There could be disjoint subset things going on here as well. Okay, it couldn't be 7, 6, 2, because 6 and 2 add up to 8. It couldn't be 7, 5, 3, they add up to 8. It couldn't be 7, 4, 1, because if that's 7, this is the 1, 4 pair in row 1. And it can't be 7, 8, 9, because they add up to far too many. So that is not 7, that is 8, I think. Now, so we're now in either this, well, we're not in that one, because 7 and 9 add up to more than 8. Oh, we could be in that one. 8, if that was 2, 5. Oh, hang on, if that's 8, we know what these are. This is what we should do. Yes, yes. So this is not, because this is 8, 2, 5. This is 1, 4, 7, because we have to preserve whatever this is, remember, is getting roped in the row. So we've got the same principle, which is this principle applying in every row. So this is 2, 5, 8. So these are not 8, 2, 5. We're not there. That, 8, 3, 4 could work. 8, 1, 6 could work. That's bizarre. Okay, but here's a weird point. Whether this is 8, 1, 6 or 8, 3, 4, those two digits add up to 7, so that digit is a 1. So that's not a 1. That's so harsh, it doesn't do anything. Okay. So what did we work out these were? 3, 4 or 1, 6. Wow. I don't know what that means. Okay. I bet there's a way that we know what this column is at the moment. But I'm wondering whether I'm actually meant to focus on those 3 squares. Let's think that through. So we know these have to be from the same set. So 1, 4 would go with 7. 1, 5 would go with 9. 1, 6 would go with 8. So this is always a big old digit. I mean, how is that helping? That's not helping at all. 2 is in one of those squares by Sudoku because of this 2 and these 2s. It could be the disjoint rule now. I mean, I really haven't thought that through very carefully. Oh, hang on. This diagonal can't have a repeat on it. Sorry. Oh, that's massive. Right, so that can't be 1, 6. Thank goodness for that. I was thinking I didn't understand how to do it. So that's 3, 4. That's not 4 in the middle. So that's not 7 anymore. And it's not 8. I've had 8 on the diagonal. This is 9, which we know goes with 5. And as so often in variant Sudoku, we get a 5 in the middle of the grid. Now. Okay, oh no, now I'm going to have to fill the... I don't want to fill, I don't want to lose my aid memoir. Oh, no. No, 267. This is a 267. I have to, don't I think? Do we think we can remember these? I'm not sure. I'm really not sure. But I don't see another option. I mean, we're now getting to the point where we're going to have to rely on our actual knowledge. It's still very much not finished, though, is it? I'm afraid. Can I do anything clever with anything here? I'm not sure. Well, okay, let's think about what set this is. But couldn't that just be a 7-9 pair? Yeah, this could be either 8-7-9 or 8-1-6. Both of those I think are valid. That's a bit scary. Okay, sorry. Maybe, can I do disjointness somehow? 9 in the bottom left. No, I mean that's doing things like getting rid of 9 from there. Okay, no, alright, so I have to think of something else. I really wish I had my aid memoirs back again. 3. How do we do this? Come on, Simon. This is not 978 or 936. So this is either 915, that's possible, I think, or 9 and then something more weird, 924 perhaps? Okay. Oh, I know what it'll be. Oh, this is really clever if this is true. Yes. Wow. Okay, this is monstrously hard. I think this is really hard. If this is 951, isn't it true to say then that in constructing the sequence that involves 2, if this was 951, the 2 sequence is going to be 276 vertical. And that's going to kill one of these squares. So this is not 951. This is 924. So this is 915. Well, these are a 1-5 pair. Oh, hang on. 924 is what I said. 924. So that's not a 2. So if we're in 924 world, 357 is a vertical. But I don't know where. 357, 186. So one of these is 186. But if this, okay, but if this is 924, so is that 186 or is it 357? I don't know. I don't know. I need some help here with the. I think I need some help with the. Yeah, I see. I can do the same thing here. If this was 879 vertical, these are going to be entropic, and one of these will be 1, 2, 3, and it will kill these. So this is not 879. This is something else. So it must be 816. Still not good enough, I don't think. So if we're in 816 world, we're in the same world as this, aren't we? So we've got 924 somewhere and 357 again. So if that was 3, that would be 5, that would be 7, and everything would work. Everything would get specified really quickly. So, oh, that's annoying. Okay, so those digits are a 7-9 pair. And somehow... Okay, so if this is 816, what's involving the 3 here? 357, isn't it? This is 357. So these are going to be 249. That's not 9. And I just need help. I just need a little bit of help from something, somehow. I presume what's going to resolve this is going to be the disjoint. And somehow these digits are going to magically resolve themselves. But I don't quite know how to do this, I'm afraid, yet. This is 147, so these are modular sets. So one of these is 369, and one of these is 258. But that's not helpful, is it? And this diagonal, so if that's 1, that's going to be a 4 or a 9. I suppose that couldn't be a 9. Have I missed a trick here? I mean, I'm sure I'm missing many tricks. I'm sure I'm missing many tricks, but I'm just wondering whether I've overlooked a really fundamental point, which is very possible. Maybe the middle box, can I do more with that? Possibly. Yeah, let's think about that. Okay, so if this is 4, that would have to be a 2. If this is 6, this has to be a 3. So this is 2 or 3. Okay, fine. What about this one? If that's a 4, that's a 7. If that's a 6, that's an 8. These are things we've learned. So this is either 357 or it's 258. And this is the same, that's 7 or 8, so that's 2 or 3. Now, is there a way? Is there a way of knowing something useful? Oh, hang on, how could that be 924? That's going to kill that cell. Oh, that would be massive. Yeah, so if that's 4, I'm claiming the only modular set. Let me look at my number pad. Yeah, the only modular set that you can make is 924. That's going to kill this. So this is 936. Boom. Boom. Wow. So that's 924. This is 357. This is 258. Right. So 2, 4 come out of those. 4 comes out of that one. 7 comes out of this one. Okay. Now, do any of these numbers map to anything along the modular? You know, yes, no, no, yes, yes. The 6 there is the same as that. That's in the same position, so that's a 1. Okay. So now we know that these are modular sets. So I now know the ordering of this box. Because that's 2, 5, 8. This must be 1, 4, 7. And this is 3, 6, 9. Now, that's now a 2. That's a 5. So we're in 2, 5, 8 world. So this is 4, 7, 1. So these are 2, 5, 8. 5 comes out of here. 8 comes out of here. 2 comes out of here. These are 3, 6, 9. 6 comes out of here. 3, 9. Now, can we somehow find a little clever little rinky-dink to help us now? I don't know. But it wouldn't surprise me if there was one. A disjoint point is what I'm expecting. That can't be a 7 because of this. Oh no, I don't see anything actually. So this is 2, 4, 9. Oh, these will be doable. This has got to preserve modularity, so that, oh, this is good. So that's got to be 2, that's got to be 5, that's got to be 2, that's got to be 1. So now, if we're in 2, 4, 9 world, 2, 4, 9, 1 is, we're in 1, 8, 6 world, aren't we? So this is a 1, 8, 6 triple. So this is a 2, 4, 9 triple. So these are a 1, 8, 6 triple. 1, 8, 6. So what were these? 3, 5, 7. So 3, 5, 3, 7, 5, 7. Somehow we need some help from the disjoint, don't we? Where do we get it from? I don't know. I wish I did know. That would be very helpful. It really would be, wouldn't it? 6s and 8s in the bottom right hand corner. Ah! 5s and 7s in these squares. Ah. Interesting, but I don't think enough. Okay, right. Here's a point regarding these. If that is a 6, in fact, I've just noticed, that's huge. So that's 6, that's 8, and this must be 2, 5, 8, which means this is 7 and this is modularity. So now that's a 7 in the corner and that's a 2. And that's a 6 and that's a 3. Now we might get somewhere. Now we might get somewhere. He says, yeah, this is 6, 1, 8. So 6, 1, 8, looking at my thing, goes with 2, 4, 9. So we know the order of this. This is 3, 5, 7. 3, whoopsie. 3, 5, 3, 7, 5, 7. We've got a 5, 7 pair here. Okay, and we know that if 6 goes with, what does 6 go with in this paradigm? 1, 6, 8. Yeah, I can do it. These are a 5, 3. So these are 1, 6, 8. So these must be 2, 4, 9. 4, 9. 2, 4. Okay, so we've got these pairs everywhere. They're pairs everywhere. So somehow, what is it? Is it going to be the disjoint thing? don't know. Okay, what are these now? 258. This is going to be the same. I'm going to have pairs again. Yeah, look, I'm getting pairs everywhere. The disjoint must help me, or I'm really in trouble. 171447. So these should be 366939, pairing up. And somehow or other, how do we do this? Something disjointedly needs to be absolutely magnificent here, and I haven't got a clue where to look. Oh no. Where do you think it's going to be? Yeah, that's a good cell. That's a 4, so that can't be a 4. So that's a 1. 174. Right. Now that should impact everything, because this now has to be 735. So that's 6, that's 8. This must be 186. This must be 429. 3592. Now, have we got the same sort of principle applying? Oh, nearly. I thought those might overlap somehow, but they don't seem to want to. 3. That's that cell. So that's 5. Which means that's 7 and that's 3. That's 3. That's 7, that's 5, and now we're in modularity land, so we can do this. This is going to finish the puzzle, I think. 8 1 6 9 4 8 2 1 4. That is a mad puzzle. It's taken me a while. I mean, that must be it must be right. There's no way that can be. You can luck into that. Oh, that's great. What a great puzzle. That's crazy. ICHTUES, that was crazy. What was going on there? That's quite mad. Absolutely mad. Probably, I don't know what I'll call the video, but possibly the maddest the maddest puzzle ever on Cracking the Cryptic. This would have a claim on that. I loved it. I loved it now. At the start, I was very terrified of it, and I think my method of looking at the number pad is probably not going to be worth much if I ever patent it. Anyway, let me know in the comments how you got on. I enjoy the comments, especially when they're kind, and we'll be back later with another edition of Cracking the Cryptic.